Hello, everybody who are already on the webinar. We'll just wait a couple of minutes for more people to join. But we'll surely get off on time, so hopefully we'll be finished on time as well. Hopefully everybody can hear me okay. Hopefully everybody can see my screen. Alexi, if you're listening, could you just confirm that you can see my
Yes.
screen okay?
Yes, I'm here. Yes, I see start slide.
Excellent. Okay. Oh, I see we've got a lot of people joining in the last 30 seconds. So that's good news. This is a particularly large webinar. We've got, I think it was over 40 people that were registered to join the webinar. So that's good news. Right. So it's 11 o'clock. Let's kick off on time and then we can finish on time as well. As some of you might know, I'm Jonathan Brindley. I think expert is going probably a bit too far, but I'm certainly an SPH system specialist. I've been dealing with this kind of equipment for good 4 or 5 years now. So hopefully you're in good hands. So today we're here to talk about the new Multibeam Echosounder system from SPH Engineering. You can see the kind of the basic webinar, what the webinar covers on the screen. And hopefully we'll make our way through that. And yeah, you'll get a really good idea at the end of whether this system is going to be of use to you in what you're doing. So a little bit about JB on Mandela Systems. As people that come to all my webinars know, I tend to do that. So a little bit about ourselves. So yeah, we've been operating for over 4 years now. Had a relationship with SPH Engineering, very strong relationship, talking on a daily, weekly basis about all kinds of different things. We're pretty much specialists in SPH Engineering. We don't really do too much other sensors. So most of our time is spent dealing with this technology, and therefore that I think that makes us quite unique in the marketplace. So we don't just do echo sounding technology. So we do deal with the full range from SPH Engineering. So that includes all those that you can see on the screen there: methane mapping, GPR, gamma ray, which is a fairly new sensor to come on the market. Those who follow my LinkedIn post would see the water sampling post that I did, where I sent a drone 250 meters away and brought a water sample back. Very useful, actually. Yeah, all these different systems, we're covering all of those. And as you'll find out later, because of this core system concept we use, it's very easy to interchange these sensors. So a little bit about the Drone Test and Training Center. It's the only one that I'm aware of that is open to everybody. It's where we test all different types of technology, so not just Echosounders, but we also test magnetometers, GPRs, and we've just recently, at the beginning of the start of this year, built what we call Sky Hut. So you'll see a little picture of it a bit later. Actually, you can just see it on the screen there in the bottom right-hand corner. And that is kind of like let's call it a ski lodge type building. And that's where we've got all the power for batteries. We've got a big screen where we can do really close one-to-one training with people. Um, but also it's really closely located to our training room, so we can do the training in the theory of it, and then we can literally walk straight onto the flying range. So it's really handy, and yeah, I'll just talk a little bit more about the detail of that. So here are the zones that we have at the moment. We've just extended the bathymetry zone, which allows us to, because of this faster speeds we're seeing, allow us to test Echosounder technology, including multi-beam, much better. We have a buried item zone where we have multiple dummy UXO in the ground, and we're able to fly over those and sort of mimic real life conditions. We have a surface target zone, and that's for the larger objects, where for magnetometry, where we people just want to gauge how the technology works and kind of what it's picking up. So that's all the way up to 50 kilogram mass. We also have which is quite unique to our range. We have a true terrain following zone. Again, we've just updated that to include other features, and that's nearly 300 meters long, and that just allows people to see how the true terrain following system works. And it is actually very important, because when you see it work, you know its limitations, and you also know what to expect. And that when you're flying over only a meter off the ground, that's really quite important. Um, we're constructing a new object mitigation zone, and that is really about how you operate the drone low to the ground in confined spaces, like fields, for instance, where you've got hedges either side, and how you can turn. We also have a sand utility zone with several different pipes sizes in terms of diameter, and also plastic, not just metal. And we're also looking at now again, if you've seen the post that we sent out, you would have seen the 30-ton JCB digger and our tractor out there just digging stuff up. I say ours, it's actually the site's. And we're hoping to have the ecology zone up and ready. And as I said there at the bottom, yeah, not forgetting, we are very rural. So we can talk about gas detection, and we can maybe mimic some of that stuff as well. So if you do get a chance to come down and just you want to see how all the systems work, it is open, an open book. You basically just say, we'd like to come down and see some equipment. You just book yourselves in, and we'll make it available. If you don't follow us on LinkedIn, it's probably a good idea, because everything we do, all the tests, if we're invited to do sort of expeditions or whatever, we always try and put the LinkedIn posts in to give people a bit of a flavor. And I do make a point of going into some detail. So hopefully that people will find that helpful. Certainly the feedback I've got is that it's really helpful. So that's a little bit about ourselves and JBUS, and how obviously what we're doing and what we're about, and we've got this test center, and hopefully helping people understand the technology. So one thing that we will talk about today is both a hardware package and a software package of how we bring this multi-beam together, this multi-beam system. Certainly on the software package side, there's a key part of that is what's called UGCS. And UGCS is the mission plan, and it's how we tell the drone what we need to tell the drone, where it needs to go, how wide the swaths need to be, how fast, and how high, and sort of how high off the ground. So it's very important in this overall system. You can see I might be biased, but my point of view, it is the best software on the market in terms of mission planning. It's very agnostic, so it's technology agnostic, which basically means you can use it on, with so many drones out there and drone manufacturers that, it is really useful. There is a comparison table online, which I found very useful when I was looking through it. So between DJI Pilot 2 and UGCS. So it's probably worth going to have a look at that, because then you start to realize how good this software really is, and what it actually can do. So in terms of how I use it, I thought it'd be quite useful just to, just explore that a little bit. So not only am I planning my areas that I'm scanning, so in this particular case, and I know we're talking about multi-beams today, but you just got to if you just assume that it's over water instead, but it's literally within 30 minutes you can learn how to use this. It's within four clicks you can essentially create your area that you need to fly, and then it's just a case of putting in making sure that you've got your altitude right and you've got your swaths right, speed right. So that bit of it's really, really easy. Um, the other part that I find really, really useful from this software is being able to just quickly put in orthomosaics. So you can send your P1 up, you can fly your orthomosaic, you can download the or upload the orthomosaic into the system, and you can then fly like real context right there and then. Not only that, with using the 2D objects, you can quickly import your lines. So you can see here that I've got my KML in there. Quickly see put in KML that maybe your customers have given you, so you can superimpose that onto your orthomosaic, and then you can literally click, 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 click. You've done your mission over that KML, and it is that simple. So I just find it really really quick and easy. And that's not to mention all the other kind of really important parts of it, like being able to see, really easily how long it's going to take you and how long it's going to be. And there are so many tools on there that are so intuitive. Like I said, within 30 minutes, you are you are able to go and fly missions. That's aside from the payloads that we're talking about today. I mean, this software in its own right is perfect for photogrammetry, for LiDAR. It can do search and rescue. It's so versatile. So if you haven't looked at UGCS before, and there are three types. There's Pro, Expert, and Enterprise, and they've all got their different aspects. LiDAR, for instance, is the expert package, as well as all the UGCS Pro stuff as well. But if you haven't, then I really would recommend you go and have a look at it and just, see if it's something that could really help you. But I use it. But the great thing about this is we use this as part of this system, so it's like you're getting the best of the best in class in terms of mission planning, and then you're able to do your mission really easily. So let's have a look at the multi-beam system then. So as you can see on the screen there, as I was told, we no longer use an OSDK for the smart cable assembly. It's now the PSDK. But we've got a PSDK smart cable assembly, which is connecting SkyHub for data and power into the drone. Again, I'm not going to go into massive detail on this because this is kind of part of your training. But we've got our PDSK smart cable assembly, which is, like I said, connects up to SkyHub. We have the SkyHub onboard computer, which is essentially the brains of the operation. We've got the multi-beam unit, which obviously you can see there, which we're calling the head. We have an arm attachment, and you can see that arm attachment. And we have a true terrain following radar, which we will talk a little bit about a bit later. But the true terrain following radar is essential for keeping the drone at the right height above the water. And obviously, I've got here a drone as part of the hardware package. But as you'll all be aware, the M400 is now out. And my understanding is that we should have, well, I say SPH should have working sky hubs for the M400 by the end of September, maybe early October, with the eye to have something be ready for release, maybe during December if we're lucky. So let's just keep our fingers crossed that is the case, because as we will see later, that gives us a lot more options in terms of, well, it gives a better flight time, and that's always a good thing. So that's the hardware package. Sorry to go, I just go back quickly. So that's the hardware package, all the hardware. So also to fly this system, we also have what's called a software package. It's really quite easy. There's three main parts to it. There's two bits of software that sit on your laptop, and there's one controller app. So it's a bit like DJI Pilot, but it's called Companion App. But it's the Companion App is what we download onto the controller, and it syncs up with UGCS and what we call CPM. Um, the CPM is has got a role. I'm going to go into that in the middle in a minute, but that's really the interface for SkyHub, the brains of the operation, which I told you about. And then we've got UGCS, which I've just been banging the drum about. So those two bits of software work together, and we then talk to the drone through the controller app, which I spoke about. So there are the three software elements, and it's the hardware package and the software package brought together that obviously make the system work. So I want to say a little bit about SkyHub onboard computer. What I talked about was it was the brains of the operation, and it's that little blue box there you can see with the SkyHub written on it, remarkably. So you can see here that we've got in terms of I don't want to don't want to get into too much detail on this, but what I do want to do is what I want to show how friendly this system is. And apart from OSDK should now be PSDK, but apologies for that. But essentially, we're taking power into SkyHub, and then we're feeding power out through a protected voltage circuit to all the different sensors. And we've got a number of different connections that we can come out of, and you'll see them on the bottom picture on the left-hand side there. You can see yellow, green, I think red, I can just see, and white and blue at the end there. And using those different connections, again, we can connect to different sensors for in terms of data, in some cases, data and power. Again, we've got LED, so to show that it's so easy to use, power is activated. You can see the power is going out to your sensor when we have a red light on, and we also have a green light to say that the autopilot is working correctly. So again, it's trying to help you along with how the system's working. So it's really useful to use and really easy to use. Another looking at the top, where I mentioned these different colors. You can see here we have a color-coded system. Without going into too much detail about that, it just makes it really easy to just plug all your sensors in. So they tend to come color-coded, and it just makes it really easy. In most cases, we're plugging in the PSDK or into the drone via the red AMA2, and the white, which I've got linked to, shown here as AM3, which the Echosounder, the single SPH and both single and dual. And then at the bottom, the RJ45, you'll know it as the Ethernet cable. For instance, we use that for GPR and also now Multibeam. So that is just showing you that we've got all different connections. It is a very versatile system, and we can connect all kinds of different sensors into it. So whatever your sensor, pretty much do it. So I mentioned about the CPM. So the SkyHub is, like I said, it's the sort of center of, and it's got a job to do. But the CPM's role is basically the interface for SkyHub. CPM is custom payload monitor. You can see it on the right-hand side there, and you can see that it's displaying all the different sensors that we've got connected. So in this case, I've got the altimeter connected via the TTF radar. I've also got an obstacle avoidance system, which you'd have seen in some of my LinkedIn posts. This can be quite useful in certain light conditions, and that sits at the front of the drone. We've also got, in this particular case, it's a GPR, but you give for Echosounder, you could still also get that as well. Connectors, so we're connecting, so CPM is and SkyHub is fusing the data and telemetry, including the RTK, and it's then allowing you to download that. The CPM also provides you with live feed. So in the MBES's case, we get the center beam single figure, and we then bring that back, and that's what you see in your CPM. So instead of seeing a GPR here on the right-hand side when you're flying, you would see the figure for the depth from the center beam. And also CPM is enabling the true terrain following algorithm, so it's also managing that as well. As you can see here, there's a little note here. It says for PPK. Now you can do PPK, but you would need a separate MLID M2, or we recommend the MLID M2, the MLID M2 antenna that comes with that. And SPH have kindly put a bracket together. So if you do need to use PPK in that solution, you can do that. As we'll find out with one of the questions later on, there's a reason why we're using a separate MLID system, and that is because of the rules, DGI rules around the access to RINEX data. But we can cover that a bit later, and I'm sure Alexia will say a little bit more about that. So one of the great things about the core system, and then what I mean about the core system is I'm talking about the Sky Hub, the true train following, and the firmware and software that allow that core system to operate. Once you've got that core system, you can interchange the sensors. So today you could be flying multi-beam, tomorrow you could be doing water sampling, and the day after you could be flying a magnetometer. So it's really, once you have that core system, you can then utilize different sensors, and it's a very easy way of interchanging sensors. And once you know how the system works, it's not difficult. It's really quite easy. So that core system, you get that versatility of going to different, being able to, you might hire a sensor from somebody here, you might have your own sensor here, but you can interchange how you want it to work. So as long as you've got your core system, you've got that flexibility. So right, okay, so that we've talked about Sky Hub, and we've talked about custom paired monitor being the interface to Sky Hub, and that Sky Hub's the center of this system in terms of how it takes data, fuses it with telemetry, and then it allows people to download, us to download it. What I want to do now is talk about multi-beam a little bit more, because that's really what we want to talk about, although Sky Hub is really important to this whole system. So this is, I do realize that there will be people on here that are far better qualified than me to be talking about this, but I just want to give people an indication of what we're talking about when we talk about MBES. So there are two types of Echosounder technology, two main types. One is single beam and one is multi-beam. As people already know, we do single beam Echosounder already, and we basically have essentially, you can see on the SPH on the picture in front of you, you have a set footprint B, and it will basically average the reading between those 2 points. So that's, you get one reading, and it'll be averaged between what it sees as an average in that footprint. So it's just essentially that whole average between that gap. With MBES, which is as its name suggests, it's a multi-beam system. It will fire multiple beams within a set footprint B, and then you get the benefit of having the averages between all of those points. So in terms of resolution, you get far better resolution, and of course it depends. For those who are in the marine industry, you can have many of these beams, and you get very good resolution. So as we will discuss, that's not quite possible on a drone, but we've got a good solution. So that's, it's not like we haven't got a good solution, because we have. So the system that we're talking about has got 16 beams. The Cerulean Surveyor 240/16, 240 because it's 240 kilohertz, and it's 16 because it's got 16 beams. Some people say 16 channels, but 16 beams. So it's firing up to 16 beams in an 80-degree swath. So that cone that you saw on the last slide, that would be the swath, and that beam degree, or the degree between the two, will be 80 degrees. Its minimum operation is 0.5 meter, and this particular system, the Cerulean 240/16, has a 50-meter maximum water depth. So you just have to bear that in mind. But saying that, that does pretty much include nearly all inland waterways and features. Not all of them, but a vast majority of them. The system itself is really light, and we'll talk a little bit more about that a bit later, and what actually that means in flight time. But it is a light system. And I'll touch on this a bit later, but it's really only the only practical option we've got at the moment in regards to this kind of system on a drone. And yeah, but like I said, I'll go into it a little bit more. The Cerulean does have an integrated IMU on board, so for pitch and roll. And I'll just jump there. We do take the heading from the SkyHub using so we're using the SkyHub system and the RTK coordinates for the heading, but we do have attached to the drone this arm that you can see here that connects the from the drone to the head of the multi-beam, and that is essentially designed in such a way to give some freedom, but not allow the head to rotate. And as Alexei informs me, rotation is not good. So the system is set up at the moment. I wouldn't say that the system is the finished product right now, but um, it might develop in the future. Yeah, Alexei.
Short comment. So as multi-beam head doesn't have a compass, we have to record to consume heading from the drone. It is why foldable arm should prevent rotation of the sensor in horizontal plane relative to the drone.
Okay.
Just a short comment.
Yeah,
Sorry.
yeah, no, exactly. Okay, no, that's good. Okay, thanks. Okay, just on the right hand side, you can see that there are, again, this is really for the YouTube video that will come out after this, but there's some quick stats on the right hand side for those people that want to know the cross-track beam width, and etc. There is quick stats on the right hand side of this Cerulean 24016. So if you need that, you can look at it. Right, so this slide is actually is for Alexei to comment on. And the MBES resolution is obviously an important element of why we use MBES in the first place. So, Alexei, do you want to make a few comments on the cell statistics and how this stacks up in terms of resolution?
So yes, for different types of surveys, we have actually different requirements for features detection on bottom, how small features or objects or holes or rocks we can detect. And here are numbers from statistics from real survey. And we can see that a small square 10 per 10 centimeters was hit at least once during survey in 99.94% of cases. So actually, such data density satisfy requirements of any surveys.
Okay. Okay. I mean, just before we go on to the IHO S44, which is the next slide, just to let you know that, and I'm saying this because it is on the left-hand side, it's the MBES calculator. If you don't want to get into like hardcore trigonometry, then you can use this MBES calculator, which we can provide, which allows you to get your resolution at the bottom. So, for example, here, estimated depth of 5 meters will give you a roughly a half a meter resolution.
Yeah,
So,
but yeah, sorry for interruption. So it is kind of pessimistic estimate because that multi-beam system emits 10 scans. It is doing 10 scans per second. So at the speed 1.2 meters per second, it will make a scan every 12 centimeters, right? So actually, a practical resolution we can check from statistics for real surveys. And in all our surveys, resolution is much better than calculated here. And also we use overlapping, of course. So in all our test surveys, we use overlapping approximately 25 and up to 50%. So every small square on bottom was hit by sound ping, actually. So here is pessimistic estimate.
Okay. Okay. The next slide, actually, Alexei, it's good. Maybe you can also comment on this special order, because I know we've had a discussion on in regard to this and the kind of standards that the multi-beam meets.
Yes, actually, it's a very popular question from customers or potential customers from hydrographic industry. They usually use as reference International Hydrographic Organization standard for bathymetric surveys. And here are uh, 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 here listed different types of surveys, starting from order 2 and up to exclusive order surveys. So most strict requirements for exclusive order surveys, less strict are for order one way and special order. So we can see that with the depth up to 20 meters, our multi-beam system will satisfy requirements for special order surveys. So limiting factor here is capability to detect features on the bottom. Again, rocks in waterways, which can be dangerous, or holes.
Okay. Okay, good. Okay. So yeah, just to show a comparison of MBES and multi-beam echo sounding data and single beam echo sounding data. Yeah, obviously we're getting better density, resolution, and coverage. You can see clearly there that the MBES is providing far better detail than the SBES. This is a trial or test that was conducted by Alex's team, and you can see that there is a definite difference in detail between the MBES and SBES. So it's evident that there is more detail, more better resolution, and data density, which you would expect. But seeing it, I think, is quite important. But as I say here, with the SBES, you can validate your MBES data with, if you do have an SBES, a single beam system, you can validate the MBES data. Yeah, as survey depth increases, then the prevailing thought is that the SBES is more accurate, and in more complex environments, sound velocity is less important. So yeah, if you've got thermoclines, for instance, in deep water, then obviously you need sound. It's good to have a sound velocity measurement for you then to be able to put that into your beamworks or whatever you're using. So that's something that is less important with SBES. SBES have dual frequency options, so you can not only just single frequency, but you can also, I think, down to around 50 kilohertz. So you can do soft sediment analysis as well. With MBES at the moment, well, with MBES it's 240 kilohertz. It's going to cut through most weeds. Only really really thick weeds, it's probably might not be able to get through. But really see that in sea conditions, in inland conditions, you should see the bottom really well. And I know that some of with the trials that Alexia has done, they have seen really good results, even though there's been kind of weeds in the bottom of the inland water features. So that's good. SBES is going to provide can provide deep up to 200 meters. Those who have used it already will know that we're getting much deeper readings from the SBES. And yeah, I mean, for lower density projects, then SBES is great. So it's not like MBES is not, it's not the silver bullet, but it can be much better than SBES in certain conditions where you do need that density. I did just touch on sound velocity there. Again, this is really only meant for those people that are new to the MBES, SBES conversation. I'm sure there'll be a few out there who are marine experts, and just excuse me a little bit. Um, but as I said there, where you do have deeper water and you do have differences in sound velocity, then it is advised with MBES that you have a water velocity measurement, and you can do that with, like, for example, I've just put here on the right hand side here, the Vailport Swift. This is readily available off the shelf, and you can attach that to, again, attach it to the drone with the same kind of core system, and go and fly it and take your readings. So that is something that we need. And why do we do that? It's because if you have a velocity that is too fast, you get what's called a smile. Again, I'm not going to go into much detail of that. I'm not a squat per se, but and also when you have the sound velocities too slow, you get what's called a frown or a sad. So you do have to be very careful, because it basically means you just get your the results you get back aren't right. So getting a good sound velocity measurement is in complex environments, like I said, with a thermocline where you've got big differences in sound velocity, it is good. And in deeper water, it's good to get a velocity reading. Also, a couple of points here on the right hand side here. The MBES does have a temperature sensor, so if you know it's fresh and salty, I suppose I'm led to believe you can make some judgments. Those experts out there will be able to make those judgments of what they think the sound velocity is. And then just as you'll see later, we do use Beamworks at the moment for the processing, and there are functions within that software where you can adjust how your data looks as well in this regard. So just to keep you aware that there are other options as well. But the general message is, if it's deep water, then you may need to look at velocity, and you might need that. Last note here, with all the trials that I've seen and also discussing with Alexei, down to 10 meters in fresh water, SPH didn't need to use sound velocity, and the results were very good. So it's only for those deeper, more complex water features that or this, for example, the sea, that you need to do that. So applications, as far as the design goes, the system suitability, let's say. So rivers and sizable cross sections. As we mentioned before, fast flowing. It's not, well, we will see it's not been tested so much, but for where you do need that density across the section, and then it can provide a solution there. Construction planning, jetties, ports, bridges, where you need good readings, good density of data, then it's going to provide a really good solution for that. Open pit lakes monitoring, and basically any open bodies, like large ponds, quarry lakes, or this kind of thing, is going to be very good for that. Post flood mapping, basically any inland water and protected water will be suitable for this solution. So moving on to sort of flying parameters. Okay, some bits here. Again, I've tried to incorporate as many of the previous questions that we've had. It's just kind of put this in, so we're covering some, the main thrust of the questions that we've got. So survey speed for this system is 1.2 meters a second currently, and at that speed, the trials that SPH have done has shown very good results. So 1.2 meters a second. You're flying the drone at 1.2 meters above the water surface, and that's based on the folding arm design and the use of the TTF radar. And to some extent, you need the head 5 to 10 centimeters below the surface of the water. So again, the setup will be so that you're flying within those boundaries, and that is giving very good results. The results that you saw earlier, and we'll see some more examples in a little while. Let's have a look. Okay, faster speed of 1.5 per second possible with degradation in quality. There's more tests required on this. It's something that I have discussed internally with the Alexis team. Maybe in the future that's something they're going to be looking at. But at the moment, we recommend 1.2 meters a second. Again, if you buy a system and you might push it and you might find that actually you don't get a big degradation at faster than 1.2. But at the moment, we recommend that you fly it at 1.2. Another question that we got was about flying this was wind and surf envelope. So if you're out of protected waters, but just bear in mind maximum wind speed 5 meters a second and swell up equal or less than half a meter. That's what's being recommended. One of the other questions: what kind of liquids could you fly this in? And people saying, "Oh, can you fly it in acidic types?" I think the answer to that question was that yes, it should be fine. If you can fly your SPH in, it should be fine to fly this in as well. But just like all these kinds of liquids or acidic type liquids, you need to flush thoroughly. Just make sure that you clean it off. Yeah, and make sure that you get as much of that liquid off as you can. In terms of accuracy, I mean, Alexi, you might want to say something about this, but we'll look at this in a minute. Actually, we've got a nice graphic to look at, but it's a close match between the SPH and the MBES. In fact, the next slide you can see here that we've got a comparison. I mean, do you want to say something quickly about this, Alexi, in terms of how they compare up?
Actually, in our tests, quite shallow tests, here maximum depth is around 11 meters in deepest point. I cannot even say what sensor is more accurate. We compared multi-beam data with single beam collected using our system, with single beam collected using Apache 3 unmanned surface vehicle, and we compared with Ocean Alpha. So actually data is more or less the same. So all measurements from all systems, which all are good and widely accepted by industry, so differences plus minus 5 centimeters. So I don't know which system demonstrate better, more precise results, more accurate, results here. But yeah, they work with the same, at least in shallow lakes and ponds and rivers, they demonstrate practically the same results. So maximum what we surveyed at the moment is 37 meters in Daugava River. But here we were not able to collect also single beam data using some alternative system, not our. But
Okay,
yeah, here results are the same.
Yeah, I mean, you can see it in the both the profiles that they're not that far away, are they? So that's reassuring. Okay. Again, another in terms of flying the multi-beam, a question that I've seen a few times now, which is what's the maximum water flow rate, of that you can fly it in. I mean, whatever it will be, but again, this is through talking to SPH. There's a lot of tests that need to be done. But whatever it will be, you'll be flying it upstream. That's what will be done. We'll just need to all keep a lookout for the tests that will be done, and then they'll be released soon. That in theory, yeah, you should be able to fly it upstream with a flown river. I think it's your tests, if I'm right, Lexi, have only been around half a meter a second. Is that right?
Sorry, I was on mute.
Yeah,
So
it's fine.
yeah, actually fastest river what we surveyed using multi-beam system at the moment is less than half of meter per second. Right. So I still suspect that for really fast reverse single beam, if it is necessary to make just cross sections, I
Yeah.
mean perpendicular cross section for the river, single beam should be more efficient. But if it is necessary to survey some part of the river, 1.5 meters per second is feasible, I think, even with the current setup. Of course, absolute speed of the drone should be reduced to not exceed approximately 1.5 meters per second relative to the water. On the segments upstream, at the segments downstream, speed should be actually increased. That will require manual editing of the water because we don't support in the mission planning tools survey grids with the different speed on different lines. But if you will see demand for that, we will implement, of course.
Okay. Okay. So, yeah, I mean, again, the SBS is got a place. So yeah, that's a proven solution. So, but yeah, just watch this space in terms of what comes out of SPH soon, and they'll be doing some trials. Yeah, everybody's asking about maximum flight time. Total kit weight in water is around 1.4 kilograms. Um, if you just look at the M350 and M400 curves, you would get what T is shown there. So M350 T is 34, and with the M400, you'll see that time should be around 46 minutes. However, what Alex's team have seen is you should be expecting around 25 minutes flight time, where they've been actually, using this in anger and actually seeing what they're getting out of their batteries. I believe that's down to 25%. So 100% to 25% it's taking you around 25 minutes. So just again, you are going to get an increase when we have the Skyhub 4 come out, and you're not going to get 46 minutes as you would suggest from, expect maybe quite a lot less than that. I've just said 30% reduction because that's pretty much what we see on the M350. But yeah, just watch this space. You kind of watch this space, but that's what I would say to expect. 25 minutes on the M350, probably, yeah, a lot less than 46 minutes on the M400 when it comes out. Just to underline again that the one of the questions we did get was, isn't there any other system than the Cerulean with the M400 that we can use? So more channels, etc., etc. And the answer to that is that currently there isn't really any other system that is UAV friendly. So so it's the best solution right now that we've got. Okay. So collection and data processing. So data collection and data processing. Three steps. But before we go into that, just a little quick note about the data login and how we do that. The raw data recorded on Skyhub is going to be recorded in what's called SVLOG format. It's going to be recorded in SVLOG format because that's a Cerulean proprietary format. And that allows us to then use something called Sonar View for a sort of initial checking. And from that Sonar View, we can export what we need for Beamworks. So so it allows us to just quickly check the data and then move that data into Beamworks for further processing. So that's how it's gonna do. So the moment if you've got Skyhub and you've got your you have CSV files in there, you'll have SegWi for GPR. You'll now see with the new firmware for CPM, you'll see Skyhub, you'll see SVLOG format available with the Cerulean. Just bear that in mind. And here is this proprietary SonarView software that I've just mentioned. So you can see there, it looks very much like LiDAR data, doesn't it? For those of the people that are doing LiDAR, looks very similar to LiDAR data, and it just allows you to see, does it look right? Have I got the right data? Is it looking right? It can just do initial checks on that. And then you're able to, once you've done those initial checks, you're able to then just export, as I said, and export that into the system. So step one, now we've just talked about how we get the data into SkyHub and the what format, the SLOG format. We do that because of the Cerulean proprietary software. We're going to collecting the data. There's the first stage, which is once we've done, we're need to go and get the data. Sorry, so we need to go and collect the data. And to collect the data, we need to do what's called a specific pattern. For that, again, for those who do LiDAR calibration, it's very, very similar to that. You're going forwards and you're going back and doing your LiDAR, aren't you? And it's very similar to that. It's called, the marine people out there, they will know it's called a path test. Sorry, patch test, I think it's called. Not that's my typo there. Sorry. But essentially, it's very similar to what you would do in the marine sector. Slightly different, but again, it's just two steps. Out and back over the same line, and then out and back with a 50%, at least 50% overlap of the waterbed, and that kind of will give the beamworks, which we're going to go on to next, enough information to process. So before we can proper clean up data and process it and then export to the products we want, we need to calculate corrections within the system, and those corrections are pitch, roll, and heading. And using that patch test, that the beamworks, what's called auto patch, will do that calculation for you and get all those angles done, so that when you take it into processing, everything makes sense to the processing software. So that patch test we do is so that we can then take that data and calculate angles that we need to then do the processing. And that's all done at the moment through Beamworks Auto Patch. Yeah, do you want to say something on that,
Jonathan,
Alex?
yeah, Jonathan, I'm very sorry. Small correction. You don't need to repeat that test, I mean data collection, using described pattern if you don't change configuration of the system. So here in SPH, we still use calculated correction angles collected in June for many dozens of surveys. So we use the same system, assemble it exactly in the same way, so we can apply the same correction angles.
Okay, yeah, understood. Yeah, so yeah, I forgot to mention that. So essentially, you're setting it up once, Alexei, and then you're able to use that exactly the same setup next time and the time after that.
Yes, 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 and maybe as we consume heading from the drone, maybe if you will do next survey quite far from the place where you collected data for patch test, maybe you will need to repeat data collection
Okay.
for it. Yeah, because heading readings from the drone can have a different error. But actually, that correction angles, reflects the small errors in the system setup. I mean, mechanical errors.
Okay. Okay. Good. So yeah, so we are to practically speaking, we're using Beamworks Auto Patch to calculate these angles, which practically speaking on a I'd say for most projects would only need to be done once, and then you can use that setup in the future. So it's just done once for pitch, roll, and heading, and then you set it all up the same, and you're ready to go. Step 3 is process to outputs. So once that auto patch has been done its job, we can then use auto clean. Again, this will be in your training how all this interacts. It's a file transfer. It's using that corrected data that we've just created, and if we're then doing the final processing to the data, cleaning it, putting filters on the data, and then removing what we don't want, and making it all look presentable. And then we're able then to export that in LAS and also elevation data as well. And that kind of data can be taken into all kinds of other programs as well. So yeah, it's all kind of the sort of standard product you'd expect from this kind of technology for use for reports and all that kind of stuff. One thing that is probably, well, what good thing to mention is that alongside the Beamworks, there is also work being undertaken on HydroMagic. And for those who already use SPH, you'll know that HydroMagic is what we're using for the SPH systems. But the MBES support is currently in development and will be out soon, so that should be helpful to those who already have HydroMagic. And it will include a patch test facility as well as the processing capability. So this is kind of just a watching brief, but it will come, and it's just hopefully just a matter of time. I believe they're nearly there. So here's some data examples, and maybe yeah. So this is a lake. My understanding is this is a lake quite close to the office in Riga. So this is really just to give you an idea of the kind of resolution that you could expect from the MBES. Alexi, if you want to say anything on any of these, then please just interject. As you can see here, these are all displayed in Drone GIS, which is a very handy GIS system if you've not used it. Very easy to use. So that's
Yes,
the lake.
I will put a link to Drone.js into chat if
Okay.
I can use it.
Yeah, that'd be useful. It is good. Another data set, which is where it's in a quarry lake, but there is a story behind this actually, and I'll steal your thunder here a little bit here, Alexi. But I think my understanding is when Alexi first saw this data and saw all the pits in the bottom of the data, he thought it was an error. And then they checked the data and found that actually it wasn't an error; they were there. So it was very accurate, and the detail that you see there with the pits are absolutely there, and they saw that with other data. So yeah, I mean it's the resolution that you're able to get from this MBES system is, it's not got all the channels that you would get with marine system, but it's it's still be able to provide a very good output. Data set example 3 is a very, well, seemingly a very deep water channel, and again, this is you can see this is kind of like an estuary to a river, and yeah, very deep, but again, used in auto clean. And then just to finish off here, I just thought it would be, again, just interesting to let's go back and compare the MBES data to the SBES data. You can clearly see the detail that you achieve using the multi-beam. It's stark. I put this line in there just to make it absolutely obvious, this dotted line, but the MBES is providing something we've never had before, which is really great to see. I mean, I've heard some people say it's a game changer. I'm not sure about that just yet, but there's obviously a lot of interest in this system for yeah, protected waters, ports, and so on. So no, it's really quite good. So yeah, let's get down to the nitty gritty. So in terms of the cost of the system, so it's actually looking at the cost. It's very similar to what we have with the dual frequency kits at the moment. It's not that different really. So recommended retail around 25K. That's the complete kit, including training. So not that far away actually from dual frequency systems. And as I said, that's including everything. Other than the drone, you need to buy the drone yourself. But apart from that, one of the slide to include here is that because there are also always developments, certainly with trying to increase speed, and there might be some developments in terms of the housing of the arm or so on. So SPH have kindly offered to replace free of charge any significant changes to the mounting up to 12 months from the date of purchase. That's good. That's pretty good. And also, yeah, data processing support for the first project. So if you do fancy one of these systems, you can be assured that if any design changes are made to the ARM system in the first 12 months you get it, you will get a replacement of the up-to-date ARM and sensor system absolutely free of charge. So that is actually really, really good. I hope you all see, you can all see that's a pretty good deal. So that's the end of the presentation for this. I do have now a number of questions that we've added in that have been asked before, and this is where Alexi can add maybe some flesh on the bone. But one of the questions that we've had previously asked was any plans to develop a real terrain following feature for the bed surface, i.e. spacing will vary between depth zones. So I mean, feel free to answer these questions, Alexei, if you think there's anything more to say, but it says about the algorithm there on the screen.
Yes, I can explain. I can explain the problem. Actually, can I share my screen? Oh no, I don't have rights. Jonathan, can you enable for me? You maybe need to make me presenter.
Yep, there you go.
Okay, great. Thank you. So, do you see my screen now?
I don't see your screen.
Um,
Yes, I can see. Yeah,
okay,
sure.
okay.
Can
So
you?
it is a full survey of the Daugava River and forgot the name of that Koknes stream joint, and you can see what we will have in case if we use
I don't think I can see your screen, Alexei.
sorry.
I don't think I can see your screen.
Interesting. I can try again. Entire screen share. And now?
It says, yeah, we can see it now.
You can, right?
Yes, we can see your screen.
Great. So here you can see what we may get if we use too wide distance between survey lines. So it was planned with 50% overlapping, as I remember, for that particular survey, for some average depth of the river. Here in deepest point is 37 meters. But here is very shallow area here, and we can see gaps in the data because swath angle is fixed. It means shallower means more narrow line on the bottom we can cover. So in ideal world, the same as on manned boats, we should correct survey lines to guarantee that we will cover all bottom with specified overlapping between lines. So that means that we need to implement dynamic change of the survey path on board of the drone. I cannot promise that we will implement that year, so current recommendation is to split survey area between zones with more or less similar estimated depth, at least without dramatic changes like here, 37 and just a couple of meters here. But it will be useful and we will do that. And
Okay.
actually, flight planning will be greatly simplified. You will need just mark survey area and start drone, and it will plan all survey lines automatically. But currently, yes, if you plan it, if you don't know estimated depth, or if you plan to wide to big distance between survey lines, you can get picture as here.
Okay. Yeah, that's useful to know. Uh-huh. Okay, can you see my screen again?
Yep.
Okay. So next question, next question. How is the distance measured between the drone and the MBES head?
Yeah, actually, I can comment again. So in current published version of our software, we recommend to use fixed offsets for vertical and horizontal separation of multi-beam head relative to RTK antenna. So that fixed offsets are valid for a speed which is close to 1.2 meters per second. But we already testing new software release which will geotag data using coordinates and elevation of multi-beam head itself. We calculate in real time real position of multi-beam head using IMU data from multi-beam head. So all Blackmagic will be done automatically, and when you process the data, you will need to use zero offsets.
That's good. That
Yeah,
makes things a lot easier.
it's really good because with the currently published release, data in turns, for example, is useless because speed can be close to zero, multi-beam head will be just below the drone, and that offsets will not be valid, of course.
Good. Right. Well, that's good then. Look forward to that. Okay, next question. Oh, well, kind of had this already, but yeah. I think it talks about your Dugava, is it, if I pronounce that right? But it's about fast foam water bodies again. And I think we've kind of covered that, haven't we?
Yeah, we already commented this also. I think it's a feasible up to 1.5 meters per second, up to 2 meters per second, but yeah, it's still the question of experiments and
Yeah.
establishing of the survey workflow mostly.
Okay. Can
Yeah,
MBES like SBES be used for grass hopping?
I think no, it's absolutely no sense because grasshopper it's about taking measurements in single point where there's a huge risk to take something to catch something in the water, seaweeds or something floating. So if so taking data from single point, it's about single beam, of course.
Can we PPK the multi-beam data? Now, we did touch on that earlier with the MLID M2, didn't we?
Yes, very answer is it depends. If you use non-DJI drone and that drone is equipped with PPK capable receiver, you can use PPK without any additional equipment and efforts. If you use DJI drones, I don't know why, but most probably just to reduce competition for the payloads, DJI decided that they will support PPK only with DJI payloads. Because Linux files, which contains all data required for the corrections, are stored inside of memory of DJI payloads. They don't allow access to that data for third parties. So if you need to use PPK with DJI drone, unfortunately, you need to use additional PPK capable receiver. In our practice, and almost all our customers use MLEAD Reach M2. It is very small receiver. I can show in my hands. 1 second. It's a receiver I hope you can see it, right?
Yes. Yep, we can see
Receiver,
the team.
antenna, and we can provide 3D model for printing as a folder for DJI 300 and 350 drones. So it costs, I don't know how much it is in United Kingdom. In Europe, it costs around 650 euros.
Yeah. That makes about, I think it's what I saw. Yeah. And in the whole scheme of things, not really, really expensive.
Yep, yep.
Okay, how rigid is the foldable arm in terms of MBES to GNSS offset changes due to the changes in UAV speed and motion?
Yeah, actually also already answered.
Yeah,
So with the current released software, we recommend to have speed 1.2 meters per second for also to use recommended offsets
yeah,
relative to GNSS antenna. So in a new release, which is already under tests, we will automatically calculate real position of multi-beam head, and all such offsets for the processing should be zero.
excellent. Yeah, that's good. That is very good. Next question: can this system calculate total volume capacity of a dammed lake, and can I merge the MBES data with LiDAR to make one single model? Yeah,
Yeah, of course, of course. As we can export point cloud and elevation data, we can do any standard operations in any compatible software. Actually, in any software which supports point clouds, standard
yeah,
formats for point clouds.
yeah.
And merging of multi-beam and LiDAR data is also very simple, because you just need to have a data in the same coordinate system and with in the same vertical data, or at least know that parameters, and you can mesh. It's a question of seconds or minutes, actually.
Okay, excellent. And this is the last question. Does the MBES system have a detachment mechanism if it gets snagged in water?
Uh, Answer is no, because any detachment mechanism, such safety mechanism like parachute. Civilian aviation doesn't use parachutes for pilots, right? And it is not good idea just to drop multi-beam system to the water. Actually, most probably you will never find it again. So we designed multi-beam head, multi-beam housing and arm to minimize probability to be catched by something in the water, including floating wires, nets, seaweeds, but 100% confidence will give only insurance. And actually it works. Past year we lost our system in water. Not because of that reason. Our operator forgot to close arm
Yeah,
lock on DJI 300, and we got full compensation from insurance company. So that works.
that's good. I did actually. I didn't. I told a fib. We've got one more, but I think we've already mentioned this before. In as much as the system is 240 kilohertz and can pretty much see, like I think we've discussed before, unless the weed at in the pond or is very thick, it's gonna be able to get good results at the bottom through the weed. Would you concur with that? Would you agree?
If we compare a multi-beam of that multi-beam system with, for example, 400 kilohertz single beam, data is much more clean over the same lake. That means that in most cases, sound penetrates through seaweeds and maybe through light sediments. But of course, 240 kilohertz, it's quite high frequency. It will not penetrate through the more or less dense sediments. So most probably you will get reflection from the surface of sediments, but that sound will penetrate through the most of seaweeds. That means that for quite a popular application of our systems, I mean sediments monitoring or sediments thickness estimation, still should be used dual frequency single beam echosounders.
Okay. Okay, well that's the last question, and as we haven't got any, I'll just check this chat. I think it might be to say that we can't see. Oh, it was yours. Okay, I mean that's the last question that I wanted to. We haven't had any other questions, and we have actually run over by, well, not that we've run over by that much, but um, I just want to thank everybody for coming on the call. Hopefully, you've learned a lot today about this new multi-beam system. This will be recording will be available on our YouTube channel. So if you go to JBUAS YouTube channel, you can see it there. Thank you very much, Alexei, for your time. I really appreciate you helping with this webinar. And thank you everybody for joining. And we'll end it there. But I hope you have a good rest of the day. Thank you, everybody, and thanks, Alexei.
Thank you. Bye.
Bye bye.